Yes, we are discussing about the decimation and interpolation, right? So we are doing some problems related to decimation and interpolation, right? So here the problem is given as signal. Consider the signal x of n equal to a power n into u of n for mod a is less than 1. So we have to determine the spectrum of the signal, first bit. And second bit is signal is applied to a interpolator that increases sampling rate by a factor 2. So determine its output spectrum. Determine its output spectrum, right? And then third bit is show that the spectrum in part 2 is simply Fourier transform x of n by 2. Okay. So what is the given signal? A power n into u of n. So u of n in the sense it is varying from 0 to infinity. So that first of all we have to find out the jet transform of this one, a power n into u of n. Okay, right? So a power n into u of n, that is u of n in the sense 0 to infinity, sigma n equal 0 to infinity a power n into z power minus n, that is nothing but a into z power minus 1 whole power n. This is in the form of alpha power n. So for alpha power n, here the z transform of this one is 1 by 1 minus alpha. So 1 by 1 minus a into z power minus 1 for mod a is less than 1. So mod a into z power minus 1 is less than 1. Okay. Okay. So it is obtained as z by z minus a for z is greater than a. Okay. So z transform of a power n into u power n, u of n is z by z minus a for mod z is greater than a. So we have to draw the spectrum for this one. For drawing the spectrum, we have to substitute z equal to e power j omega. Okay, so at the place of z, replace z by e power j omega. So z x of e power j omega equal to z by z minus a. So e power j omega by e power j omega minus a. As we know that e power j omega is cos omega plus j sin omega. Okay, and here e power j omega is cos omega plus j sin omega minus a. Here we are separating real terms and imaginary terms. So magnitude of x of e power j omega is equal to square root of cos square omega plus sin square omega by square root of cos omega minus a whole square plus sin square omega. Okay, so by simply substituting various values of omega, that is 0, pi by 4, pi by 2, 3 pi by 4, pi pi by 4, 3 pi by 2, 7 pi by 4, and 2 pi in this expression, so that we will get mod x of e power j omega is like this. For these values omega versus mod x of e power omega and omega, for this for these two values, we will draw the spectrum. We will draw the graph that is nothing but a frequency spectrum of this IA power n into u of n. Next one is next problem is the interpolated signal y of n, which is obtained by increasing the sampling rate by a factor 2 for a power n into n can be written as. So interpolator means x of n by l. Here by factor 2 is l is 2. So x of n by 2 is a power. So n is replaced by n by 2, x of n. So here n in n plus it is replaced by n by 2. So a power n by 2 into u of n. Okay. So for this one we will take the z transform. So sigma n equal 0 to infinity a power n by 2 into z power minus n, or it is a into z power a power 1 by 2 into z power minus 1 whole power n, or a into a power 1 by 2 into z power minus 1 whole power n, right? So that is also series. So its solution is 1 plus a power 1 by 2 by z plus a power 1 by z square plus a power 3 by 2 by z cube, like this. Okay. So its solution is 1 by 1 minus a power 1 by 20 z power minus 1 and a power 1 by 20 z power minus 1 mod is less than 1. Mod a power 1 by 2 root a by z is less than 1. Okay, its solution is z by z minus root a. How to get the spectrum of this one? By substituting z equal to e power j omega. So y of e power j omega is equal to e power j omega by e power j omega minus root a. So in the same manner, e power j omega is replaced by cos omega plus j sin omega. So cos omega plus j sin omega, right? So minus root a. So here also we are separating real and imaginary terms so that it will become y of e power j omega is equal to square root of cos square omega plus sin square omega, that is 1 by square root of cos omega minus root e whole square plus sin square omega, right? So it is a minus b whole square a square plus b square minus 2ab plus sin square omega. So it will become 1 by square root of 1 plus a minus 2 root a into cos omega. Okay, cos omega. So by substituting various values of omega in this one, so omega equal to 0, pi by 4, pi by 2, 3 pi by 4, pi, pi by 4, 3 pi by 2, like this. Okay. So by substituting these values in this expression, we will get mod y of e power j omega these values. So for these two values, we will draw the spectrum. This is the frequency spectrum. So for bit B, for B bit, the interpolated signal y of n, which is obtained by increasing the sampling rate by a factor 2. So it is the spectrum. Is the 20, is the spectrum. Okay. Next, coming to the C bit, the Fourier transform for x of n by 2 is obtained as okay. Uh, Fourier transform of x of n by 2 sigma n equal 0 to infinity x x of n by 2 into e power minus j omega 1. Okay, right? That is a power x of n by 2 j power n by 2. A power n by 2 into e power minus j omega 1. So it is obtained as 1 plus a power 1 by 2 into e power minus j omega plus a into e power minus 2 j omega plus so on. So it will become 1 plus a power 1 by 2 into e power minus j omega whole power minus 1. So it will become 1 by 1 minus a power 1 by 2 into e power minus j omega. It is nothing but e power j omega by e power j omega minus root a. Okay. So C bit is nothing but what is C bit? C bit is show that the spectrum in part 2 is simply the Fourier transform of x of n by 2. So these two are equal. So spectrum in part 2 is equal to Fourier transform of x of n by 2. So this is the spectrum of part 2. Okay. So this is about that problem. Next problem is design one stage and two stage interpolators to meet the following specifications. Okay, interpolator value is given as 20. Okay, it is given as 20. Okay, see, see, specifications given as I equal 20, and for pass band that is in between 0 and 90, and transition band is 90 to 100. Okay, and input sampling rate is 10 kilohertz or 10,000 hertz, and ripples are delta 1 equal to 10 power minus 2, and delta 2 is 10 power minus 3. This is the given information. So we have to design one stage and two stage interpolator. Okay, I is given as 20. Pass band frequency FP is 90 hertz. Stop band frequency FSC is equal to 100 hertz. Okay, and input sampling rate Fin is 10 kilohertz, that is S1 and delta 1, and pass band ripple input sampling rate that is 10 kilohertz, and pass band ripple that is delta 1 equal to 10 power minus 2, and delta 2 is 10 power minus 3. So for a single stage interpolator design, we have to design interpolator initially design a decimator with the same specifications, and then transpose the design to get an interpolator structure. So first of all, we have to design a decimator with the same specifications. So I is given as 20. So before going to design the interpolator, we have to design the decimator. That is, let us consider d equal to 20. Then the order of filter is given by order. Order is n1 equal to is the formula. Formula for finding the order of the filter. N1 equal to minus 10 log delta 1 into delta 2 minus 13 by 14.6 into delta f plus 1. This is the formula. Okay. So where delta f, what is delta f? This is nothing but FSC minus FP. Okay, FSC minus FP is nothing but delta f by Fin into 10k. Fin is 10 kilohertz into by Fin. FSC minus FP by Fin. So it is 100 minus 90 by Fin, that is 10 kilohertz. So 10 by 10 kilohertz, that is 0.001, that is delta F value. So N1 equal to minus 10 log delta 1 into delta 2, that is 10 power minus 5 minus 13 by 14.6, and delta F is 0.001 plus 1. So by simply substituting this, we'll get N1 is 2535.25 or 2536, right? So this is the formula for finding the order of the filter, that is minus 10 log delta 1 into delta 2 minus 13 by 14.6 delta F plus 1. Okay, so delta F is nothing but stop band frequency minus pass band frequency by input sampling rate, that is FSC minus FP by Fin. Okay, 100 minus 90 by 10 kilohertz, that is 0.001. So by solving this, we will get N1 equal to 2536. Next, output sampling frequency is given by the formula F0 equal to Fin by D. Fin by D. What is Fin? Fin is nothing but input sampling rate, that is 10 kilohertz. So 10 kilohertz into by D. D is nothing but 20. Okay. So 10k by 20, that is 500 Hz. Okay, what is the structure of the single stage decimator? So before the decimator, low pass filter is there, having the order of the filter, that is N1 equal to 2536. Okay, 2536 followed by decimator with the value 20. So F0, what is F0? Fin by D, that is 10k by 20, that is 500 Hz. Okay, so and the transpose of figure gives the single stage interpolator circuit of I equal to 20 is as shown in figure 20. So this is a transpose of the above figure, that is nothing but single stage interpolator. Transpose of this structure is nothing but this one, single stage interpolator. So interpolator is nothing but up, up upsampler followed by low pass filter. Upsampler followed by low pass filter. Okay, so this is equal to upsampler with value 20, interpolator with value 20, and followed by low pass filter with order n equal to 2536. So here F0 is 20 into 20 into Fin. Okay, D Fin. So I Fin. Okay, so this is about the single stage interpolator. And coming to the two-stage interpolator, consider two decimator factors, that is D equal to 2 and D2 equal to D1 is 2 and D2 is 10. Why? Because here D is 20, so we will take D1, D2 like this. Two decimation factors, 2 is 2, 1 is 2 and another one is 10. So F1 equal to, what is F1? Fin by Fin by 2. What is Fin? 10k by 2. That is 5 kilohertz, and F2 is F1 Fin by 2 D1, that is 2 10k by 2, and here F2 is 5. This is F2 F5 kilohertz by 10. Okay, that is 500 kilohertz. Okay, so coming to the first stage, pass band. The pass band range is from 0 to 90 hertz. Transition band range is from 90 hertz to F1 minus FSC. So 90 hertz to F1 minus FSC is what is F1? 5 kilohertz. FSC is 10 kilohertz. 5 kilohertz minus FSC is FSC. What is FSC? FSC is from 90 to 4.9. 4.91. Okay, and delta F1 is FSC minus F1 by, so this is F1 minus FSC. F1 is 5 kilohertz, FSC is 10 kilohertz. So by simply substituting it will give you 5 kilohertz, almost all 5 kilohertz. So FSC minus F1 is delta F1 equal to FSC minus F1 by Fn. So that is 4.91 minus 90 by 10. That is 0.482. 0.482. Okay, then the order of the filter is given by using the formula. Okay, so what is that formula? Minus 10 log delta 1 into delta 2. Okay, 10 log delta 1 into delta 2 by delta 2 minus 13 by 14.6 into delta f plus 1. So it will give n1 equal to 40 plus 40.01 by 14.6 into 0.031 plus 1. Here delta 1 dash is equal to delta 1 by 2, that is 10 power minus 2 by 2, that is 0.005, and this is delta 1 dash into delta 2, that is 10 power minus 3 minus 13 by this one plus 1. So that n1 will get 40.01 by 14.6 into 0.482 plus 1, that is 6.685 is approximately equal to 7. So n1 equal to 7. So first stage n1 equal to 7. In the same manner, we'll find out n2 for the second stage. So passband range is from 0 to 90 Hz. Transition band is 90 Hz to f2 minus 100. So f2 is 500 Hz. 100 calculated. This is f2. 500 kilohertz minus 100 kilohertz. So 400 kilohertz. Okay, and delta f2 equal to FSC minus FC. FSC minus F1 by Fn. So it is 400 minus 90 by 10, that is 0.031. So order of the filter is minus 10 log delta 1 and delta 2 dash minus 13 by 14.6 and delta f2. So delta 2 dash is equal to delta 2 by 2, that is this one. Excuse me. So nt equal to minus 10 log 10 power minus 2 into 0.5 into 10 power minus 2 minus 13 by 14.6 into delta f is 0.031 plus 1. So it is approximately equal to 90. So nt, right? Nt is 90. So the second stage calculator of Decimator by a factor d1 equal to 2 and d2 equal to 10 is illustrated like this. So before the Decimator, low pass filter is introduced. This is the thing. So d1 equal to this n1 value is 7, right? N1 is nt is 90 and dt is not equal to f by 20, right? This is two stage interpolator. Okay, next the reciprocal of this one is two stage interpolator, right? This is the two stage decimator. So reciprocal of the transpose of this one is two stage interpolator. So I1 is 10, then LPF low pass filter with order 90. Okay, 10 into f in. So I2 equal to 2 into with the order 7. So it is 20 into f1. So f0 equal 20 into f1. Here f0 equal 10 into f1. Okay, this is about the design of one stage and two stage interpolators, right? Next, coming to the consider the ramp sequence and sketch the interpolated and decimated versions with a factor of 3. Okay, so the ramp signal is denoted as R of n equal to n. R of n equal to n for n is greater than or equal to 0, otherwise it is 0, right? So R of n equal to n for n is greater than or equal to 0 and is 0 elsewhere. Okay, so the ramp signal is represented like this. So R of n is R of 0 is 0, R of 1 is 1, 2, 3, 4, like this it will be represented. Okay, with unit ramp function. Okay, so what is given if a decimated factor, the sketch its interpolated and decimated versions with a factor of 3. Okay, so first of all, the decimated signal is given by y of n equal to R of mn, R of mn, where m equal to 3. So it will become y of n equal to R of 3n, right? R of 3n. If n is 1, this is this one. If n is 2, this one. If n is 3, this one. Okay, 1n, 2n, 3n. Okay, right? So that is the decimated signal with factor 3. And interpolated signal, it is represented by y of n equal to r of n by L. So here n is 3, so it is n by 3, n by 3. Okay, n by 3. So 3, 6, 9, 12. At these places, it will appear. Interpolated signal with factor 3. Okay, so these are the decimated and interpolated factor 3 sketches. So next, explain the need of sampling rate conversion. You have to know about the sampling rate conversion. Okay. So, or otherwise it can be asked like this: explain the fractional sampling rate conversion with the time domain and frequency domain relationships. Explain the fractional sampling rate conversion with time domain and frequency domain relationships. Right. So here, the sampling rate conversion by a factor L by M can be achieved by first partitioning the interpolation and then performing performing the interpolation and then performing decimation by a factor m. So sampling rate conversion by a factor L by m can be achieved by performing first interpolation and then decimation by a factor m. Okay, here which one of K is anti-imaging filter and H2 of K is anti-aliasing filter, right? So first of all, we are performing interpolator. That's why we will get anti-imaging filter, and then we are performing decimation. That's why we will get anti-aliasing filter. Are operated at the same sampling rate. Okay, hence can be replaced by sample simple LPF can be replaced by simple low pass filter with a transfer function h of k. So that the cutoff frequency of a low pass filter is omega c is equal to minimum of pi by L, comma pi by m. Okay. So the cutoff frequency of the low pass filter is omega c is equal to minimum of pi by L and pi by m. Okay. So let d by I be the sampling rate conversion factor. D by I. Okay. D by I. See here, sampling rate conversion means L by M or I by D. Okay. L by M or I by D. Let D by I be the sampling rate conversion factor. That implies T dash by T is equal to D by I, or T dash by T dash by F is equal to I by D. So f dash equal to I by d into f, or t dash by t equal to 1 by x, or 1 by t dash, 1 by t dash is equal to 1 by t. So 1 by t equal to f. Okay, here it is interpolator and this is decimator. First we'll perform the interpolation operation and then performing the decimation operation. So interpolation operation means upsampler followed by low pass filter. Okay, and the decimation means filter followed by decimation factor. So x of n, and this is interpolator, and followed by filter. So this is f double dash equal to I into f. Okay, so this is y of k, this is h2 of k. So this is I by d into f. This is here it will be multiplied. Interpolator will be multiplied with this f, and decimator will be divided by this f. Okay, I by d into f. Okay, right? This is y of t. So this is cascading frequency sampling rate converter. This is called cascading frequency rate converter. Okay, then x of n I is there. This is h of k, and h of k is nothing but f dash. That is f dash equal to I into f. So it will be given to the decimator. So decimator with f equal to I by d into f dash equal to I by d into f. This is y of t. This is efficient way of fractional sampling rate conversion. This is nothing but the efficient way of fractional sampling rate conversion. So from figure 1, so this is the figure 1. the fractional sampling rate conversion is achieved by increasing the sampling rate by I, and then it is decreased by decimator D. So cascade connection of interpolator and decimators are as shown in the figure 1. Shown in the figure 1. Okay. Okay, so this is the efficient way of fractional sampling rate conversion. So in figure 1, the fractional sampling rate conversion is achieved by increasing the sampling rate by I, and then it is decreased by D. So cascade connection of interpolator and decimator is shown in this figure. So H of K is the low pass filter which is obtained by combining the filter H1 of K and a H2 of K. H of K is nothing but low pass filter which is obtained by combining which one of K, and these two are combined so that it will become H of K. Okay. The low pass filter is operated at the E of the characteristics of low pass filter H of K is given by H of e power j omega is equal to I in I is equal to I, where mod omega double dash is less than or equal to minimum of I by pi by I and pi by t, or it is equal to 0 elsewhere, where omega double dash is equal to 2 pi f into t double dash. So 2 pi f into t double dash means t by I. Okay, t by I. Since t double dash is t by I, that's why it will become 2 pi f into t by I. The sampling rate f double dash is I into f. Okay, so time domain representation, the sequence obtained at the output of sampler is yi of L, that is equal to yi of L is equal to x of L by I, where L is varying from the L is 0 plus or minus 2I, etc. Otherwise it is 0. And the sequence present at the low LPI filter is that is h of k is given by y2 of k is equal to sigma L equal minus infinity h of k minus L into y1 of yi of L, that is sigma L tends to minus infinity h of k minus Li into x of L. That is equation number 2. By downloading the sequence y2 of k with a factor of d, we can obtain the sampling rate converted signal yd as yd equal yd into d into d. So our yd equals sigma L equal minus infinity to infinity h of dd minus Li into x of L. That is equation number 3. Okay. And frequency domain relationships are like this. We'll explain again in the next class this topic. What is this topic? We'll again discuss this topic in the next class. Okay, sampling rate conversions. Okay, with this I'm concluding the today's session. Okay, thank you.